Let's talk about electrical engineering and complex numbers. First, welcome to ELEC 202. I'm recording this on December 28th, 2017, only a few days before all of you start a new stage on your journey towards electrical engineering. Congratulations about finishing successfully ELEC 201 in electrical engineering. Once we pass the beginner stage where we were last term, everything is a complex number, currents and voltages. Instead of ohms, of henries, and of farads, we will use impedances, and impedances are, you guessed, complex numbers. What about power? Well, power is now also a complex number. Complex numbers like the ones we saw in high school, well, yeah, but what we saw in high school is not enough. Remember what the oracle told Neo. Know thy complex numbers. And that is exactly what we're going to do, and we will begin with imaginary numbers. A note before we begin. For mathematicians, I is the imaginary unit. You square that, you get -1. But for electrical engineers, a lowercase I is electric current, so we use J instead, and that is the standard use in electrical engineering. J squared is -1. The following story is made up, of course, but ridiculosity is something that we humans remember, and that is the purpose of this. For ages, people had known that whenever you squared a number, you would get a +1. X squared is positive. So much so that when for the first time someone said, what if there is a number j whose square is -1? Of course, other people said, yeah, sure, the Easter Bunny is also real, and so is Santa. Actually, the person who asked that question was the Italian mathematical genius and grandfather of infinitesimal calculus, Gerolamo Cardano. He was the one actually who said that what if there is a number j whose square is -1, and he himself thought, man, I am imagining this j. It is an imaginary number. Imaginary, right? Yeah, he insisted. Imaginary, it's a figment of my imagination. Imaginary, I have imagined a number j whose square is -1. But imaginary, why? Well, because when I square it, I get a negative number, of course. Well, it's a imaginary for real or a prejudice. Think of it. If I say that j is imaginary because when I square it, it's negative, what about j3? Square j3. Oh, that would be j squared times 3 squared. That is -1 multiplied by 9. That is -9. So j3 squared is also a negative number. If I'm going to call j an imaginary number because its square is negative, then I have to say that j3 is also imaginary. What about -j3? Square it. When you square that, you get j squared multiplied by -3 squared, and that is, again, -9. So you see, every time you multiply j by any real number, positive or negative, you get a number whose square is negative. You get an imaginary number. That means that there are as many imaginary numbers as there are real numbers. For every real number, I multiply that times j, and I get an imaginary number. Real and imaginary, right? Sure. Because we've been calling this new breed of number imaginaries by counterposition, the whole numbers have to be known as real numbers, sure. What if we add them together? The result is neither real nor imaginary. What we get is a more general and powerful type of number. What number is that? A complex number. A number that has a real part and an imaginary part. Remember, this is only a representation of that complex number, right? Right. What? A representation. We will identify, use, and explore 6 different ways of representing any complex number in our study of electrical engineering. We better get on with it, right? Let's explore the difference between what is an object and the way we represent it. In everyday use, some people think of a person as fingerprints or perhaps a social insurance number or a DNA pattern. Even a picture can represent a person, but none of them is really the person. Those are representations of the person. The same is true with numbers. Nobody has ever seen number 3. We've seen 3 oranges, 3 pineapples, 3 bananas, right? But the number 3, the abstract number 3, no one has seen that. We use symbols to represent number 3, and those symbols have changed along our history. Let's have a look at it. Ancient Romans used to represent number 3 like that, and ancient Chinese this way. And different regions of the planet have been using different symbols to represent number 3 until Europeans chose the set on the very top, and since then the whole planet have followed suit and represent number 3 this way. But in other planets where intelligent life may thrive, I bet good money that they are using some other symbol to represent the same abstract concept as number 3. For those Trekkies in my audience, number 3 is represented in Klingonese with that symbol, the number 3. Neither of those is 3. Those are symbols we use for that. Real numbers are pretty straightforward and simple, but complex numbers, they have more than one representation that we use at the same time. How? Well, this is one way of representing a complex number, the binomial representation, where we see the real part and the imaginary part. 3 plus j of 4. Another one. Do you remember that real numbers are represented by a point on an infinite line that we call the real axis? Remember that? To every point a real number, to every number a point on that real axis. Because there are as many imaginary numbers as real numbers, remember, multiply a real number by j. We represent all imaginary numbers also on an infinite line that we call the imaginary axis. What about complex numbers? We do something similar. We represent every complex number by a point on this complex plane. So you realize immediately that for every real number there is an infinite number of complex numbers. So complex numbers are more abundant than real ones, even though both are infinite. We're going to represent then a complex number by a point on that complex plane, or we could represent it by the coordinates of that point. Let's say 3 and 4. That representation of the same complex number is what we call the rectangular or Cartesian representation of the complex number 3 plus 4j. Another way? Sure. We can represent that same complex number that corresponds to that point by the position vector that goes from the origin of the complex plane to the assigned point. And that vector has a length 5 and has an angle with the real axis 53 degrees, and we say we represent the same number with those two, 5 with 53 degrees. We call that the polar representation of the very same number, and 5 is the absolute value of that number, and 53 is the argument in degrees of that number. We could also write that argument in radians, of course. One more representation, sure. Do you remember Euler's numbers? I'm pretty sure you do. Whenever you find the exponential of an imaginary number jx, what you get is a complex number written like this. Cosine x plus j sine x, a complex number. Of course, for that expression to make sense, x has to be given in radians. Absolutely. Well, in other words, the exponential of an imaginary number jx is a complex number. Let's see what other conclusions we can extract from that definition. Let's represent the Euler's number on the complex plane. The Euler's number, here it is. The real part, cosine x. The imaginary part, sine x. First question, what is the length of that vector? What is the absolute value of the Euler's number? Pythagoras, right? Sure, that is cosine squared plus sine squared, and that is 1. Square root of 1, that is 1. And Euler's number absolute value is a 1. What about the argument? That angle, theta? Well, remember SOHCAHTOA. The tangent of that angle is sine x divided by cosine x. But you also remember that sine divided by cosine, that is tangent. Absolutely. So theta is the arc whose tangent is the tangent of x. What a tongue twister. Well, that means that theta is x. In other words, an Euler's number, exponential of jx, has an absolute value of 1 and has an argument of x radians. Super. What about if I multiply an Euler's number by 5? There. The real part would be 5 times cosine x. The imaginary part would be 5 times sine x. What is the absolute value? Oh, the absolute value would be 5. Yeah. And the argument? Let's divide 5 sine x divided by 5 cosine x, and we get exactly the same angle as before, x. That means multiply by 5 an Euler's number, and what you get has an absolute value of 5 and the same argument as before. That is another way of writing in polar form the same number, but we're going to call this an exponential representation. So those are only representations. We can represent the same number by a point, by a vector, things that we're going to be using a lot in electrical engineering, or with symbols this way, in binomial form, in rectangular form, in polar form, or in exponential form. When? Which one do we use? There is one rule, convenience. We will use one or the other depending on what we're using the complex number for. If we're representing impedances in ohms, we use rectangular mode, or if we need to add or subtract complex numbers, right? But if we are representing currents or voltages, we're multiplying or dividing complex numbers, it's going to be more convenient to use polar form or exponential form. We shall see. How do we go from polar to rectangular and back? Let's see. Real axis, imaginary axis. There is our complex number that has that absolute value m and the argument theta. What is the real part? Remember SOHCAHTOA? Remember SOHCAHTOA? Sure. The real part is m cosine theta, and the imaginary part is m sine theta. That's how you go from polar form to rectangular form. That is the complex number m cosine theta plus jm sine theta. You can factor out m. But the number in parentheses is an Euler's number. Indeed, we realize that that exponential representation is equivalent to the polar representation as long as theta comes in radians, a real number. Euler's identity. And how do we go back? If what we know is the real part and the imaginary part, of course, the length of the vector, which is the absolute value of the complex number, is given by Pythagoras, right? That is simply square root of a square plus b square, real part square plus the imaginary part square. And the argument, SOHCAHTOA. That is the arc whose tangent is the imaginary part divided by the real part. And that's how we go from rectangular form to polar representation. But once we have numbers, we need to do something with them, and we will do. We need to add them, subtract, multiply, and divide. How we do that? Let's begin by multiplying by a real number. 3 times a plus jb. We distribute the multiplication over the sum, and this is what we get. We get a complex number that has 3 times the real part and 3 times the imaginary part. Let's do that graphically. Check it out. This is the number AB, has a real part A and imaginary part B. We multiply that times 3. We get another complex number that has 3 times the real part and 3 times the imaginary part. We plot the result, and we get a complex number that is 3 times longer in absolute value, but it has exactly the same argument. All we're doing when we multiply a complex number by a real number is stretching that number. That's what we're doing. Multiply a complex number by a real one, and you stretch that complex number by 3, by 5, by 10, whatever number you're using. What if you multiply times the negative real? What you're doing is stretching that by the absolute value of the real number and flipping it about and pointing that in the opposite direction. Tutorial time with Euler's numbers. Let's do something with numbers. Compute the exponential of j 0.2 radians. That is cosine of 0.2 radians plus j sine of 0.2 radians. That is 0.98 real part plus j 0.2. Imaginary part 0.2. Let's do that with a calculator, shall we? Exponential of 0.2j, enter, and we get absolutely the real part is 0.98 and the imaginary part is 0.19866 something 0.2. Well, now that I'm doing that using the calculator, using the HP prime, wait a minute, the what? The HP prime is the top of the line of calculators produced by Hewlett-Packard, and in my opinion is probably the most powerful calculator that I ever seen and worked with. And let me tell you, I have used almost every single calculator that has been produced. Let's see how we use the HP prime. Wait. The HP prime again? I don't have one. Oh, yes, you do. Downloading the emulator of the HP prime either for Mac OS or Windows is free. Google it, download and install it. You can even purchase for only a few dollars an emulator for your iPhone or for your Android or tablet or whatever, right? And the calculator itself is not that expensive. Now let's proceed. You have the HP prime. How do we deal with complex numbers? Well, the very first thing, I go to the settings of home. Blue shift, settings of home, and down here you say complex numbers can be represented in binomial form or in rectangular form. Let me leave it as a binomial. Later on in the course I'll be using rectangular all the time. By default, the calculator knows who is I. You square I and you get -1. But we will define j. J colon equal I. I am defining j as I, the imaginary unit, so that I can write that in electrical engineering, right? Correct. Let's proceed. Observe that expression. I am operating, adding two complex numbers and dividing that by the sum of other two complex numbers. I am adding 5 with the exponential of 0.2j. That is a complex number in exponential format with another number in binomial format, 3 plus 4i, and dividing that by 7 with 17 degrees, a number in polar form, plus, parentheses, 5, -7, and number in rectangular form. I type enter, and the calculator knows everything that needs to be done and says the result has a real part 0.4 and an imaginary part 0.6. Oh, but I don't like that in rectangular mode. Show it to me in polar form. Piece of cake. On the keyboard, you click Shift and that angle thing under the multiplication key, and voila, you have the absolute value of 0.7 and the argument 55 degrees. How do I know that 55 is degrees and not radians? Oh, because up here, I realize my calculator is in degrees of form. Now, polar and Euler's, right? All right. When I write 5 exponential of j.2 radians, right? Like that, what I'm doing is multiply by 5. That is exactly the same as the polar representation of 5 with 0.2 radians. That's right, they are equivalent. We know what happens to a complex number when we multiply that by a real number. We stretch it. What happens when we multiply a complex number by an Euler's number? Let's see. There you have 7 with an argument of 0.3 radians, right? That one. If I multiply that by an Euler's number of exponential of j.2 radians, the result has the same absolute value, but the argument has been increased by 0.2 radians. It is as if I have rotated the original number by the angle, the argument of the Euler's number. That's what happens. Multiply a complex number by an Euler's, You keep the magnitude, you keep the absolute value, you keep the modulus, and you rotate the number by the value of the Euler's number. Now, when we multiply a complex number by another, we are stretching and we are rotating. When we multiply 7 with 0.3 radians, with a complex number 2 with 0.5 radians, we are stretching 7 by 2, and we are rotating that number 7.3 radians by 0.5 radians. It's stretch and rotate. I want you to visualize a multiplication of two complex numbers as a stretch plus rotation. Why? Because we shall see we have Ohm's law with complex numbers. Amps times ohms is volts. You stretch the current by the value of the impedance Z in ohms, and you rotate the current angle beta by the angle of the impedance theta. Now let's visit another definition that we have seen with complex numbers, a conjugate. Given the real axis, whenever we have two complex numbers where they are the mirror image of the other, they share the real part A, but their imaginary parts are opposite to one another. We say that they are conjugates of each other. The conjugate of AB is A negative B, or the conjugate of A negative B is AB. And then what? I will show you a little trick that is very convenient in electrical engineering. When I multiply a complex number AB by its conjugate A minus B, see what happens? A squared minus JB squared plus JAB minus JAB, negative JB squared, that is positive B squared, right? And JAB minus JAB is going to cancel out. What you get when you multiply a number by its conjugate is a real number. What number is that? Pythagoras. What you're getting is the absolute value of the number squared. The absolute value would be square root of A squared plus B squared, right? Correct. Multiply a complex number by its conjugate and you get a real number, the square of its absolute value, something that will be very useful to us very, very soon. When you multiply the voltage times the current to compute power, well, what we do in complex numbers, we multiply the voltage by the conjugate of the current, and that gives us the power. We shall see why and how. Multiplication in polar. We have those two numbers in polar forms, right, represented in exponential format. We use the commutative property of multiplication. Those are four numbers, and we say the result is this one. We multiply the absolute values and we add the argument. That's how we multiply in polar forms. Again, let's do the same trick with complex conjugate numbers, but in polar form. Those two numbers, conjugate of each other, have the same absolute value, but their arguments have opposite signs. The conjugate of m beta is m negative beta, and vice versa, right? Multiply conjugate by a complex number, and what you get is what? You get the square of its absolute value. Same as before, and you know why that's important to compute power. Soon enough, we will learn we multiply the voltage as a complex number by the conjugate of the current as a complex number, and that is going to be power soon enough. So how is it that we add complex numbers? Apples with apples and oranges with oranges, right? Those two complex numbers, to add them, let's reorganize that, and we add the real parts and we add the imaginary parts. I am factoring out J. That's how we add complex numbers. An example, 3, 4, and 2, 3. What is the sum of that? You say, well, that's a piece of cake. That's going to be 5, 7, right? Let's do that with a calculator. Check it out. 3, 4 plus 2, 3. Absolutely, that is 5, 7. Yeah. Super. How do I add numbers in polar form? Let's see. I'm adding 2, 4, and 6, 2. Let me do that graphically for a moment, right? That's going to be, I know it's going to be a 6. You know that, I know that. That is going to be 2 plus 6 is 8, 4 plus 2 is 6. Let's do that graphically. Here on the complex plane, there is just the first number, 2, 4. And the second one is 6, 2. Well, the result is going to have a real part that is 8 and an imaginary part that is 6. The result, graphically, is going to be given by this vector. Remember that vector also represents that complex number. We arrive at the conclusion that we can add complex numbers graphically, adding their vector representations the same way we added vectors in physics. And that's going to be wonderful, and we will use that a lot in electrical engineering. We add complex numbers graphically as vectors. And subtracting as vectors? Sure. If we're going to subtract a minus b, those are a and b represented as vectors. What we do is we add a with the negative of b. A plus the negative of b. The result is going to be this one, right? Right. But we can obtain that same result as the vector that joins the tip of b to the tip of a. That's how we're going to subtract graphically a minus b. In rectangular, how do a division? You say, why do I want to do that? I have a calculator. Yeah, sure, but sometimes we have a division where we don't have numbers, we have symbols. In an exam, in that case, we need to do that by hand. What we do is we multiply and divide the conjugate of the denominator, right? Like this. Divide AB by CD. Multiply and divide that number by C negative D, like so. Why? Because then the denominator will become a real number. Remember, C squared plus D squared? And we identify what is the real part of the result and what is the imaginary part of the result. That's why. Division in polar. In polar, that's a piece of cake. We just divide the modulus, the absolute value, and we subtract the arguments. Tutorial time 1. This is not really an exercise of this term, but rather of the previous course. But it will allow us to warm up. Let's say I have that circuit, a source, and 4 resistors, and I ask you, what is the equivalent resistance seen by the source? And you say, oh, that is just R1 in series with a parallel of R3 with a series of R2 and R4, right? And that is correct. And if I divide the voltage source value by that equivalent resistance, I get the current in the source. Do we agree? Sure. We are really in sync. Let's see. The first top hat question. Those are the values of the resistors, 2 ohms, 4 ohms, 16, 12, and the value of the source is 20 volts. You don't really need a calculator to tell me what is the value of the current in the source. I'll wait a few seconds and you come up with an answer, right? Those of you in my classroom will be asked this question in top hat for grades. Second question, same circuit. What is the power absorbed by the source? Mind the sign. I'm asking for the power absorbed by that source in watts. Third top hat question. In that circuit, find me what is the voltage of the node 1 at the top with respect to the reference. Now let's go back to a tutorial time before I ask you 6 more top hat questions. Let's assume for the time being, and this way we'll prove in the rest of the course, that we can represent a voltage by a complex number in volts, that we can represent a current by a complex number in amps. Also, let's assume that we can represent a resistor, an inductor, and a capacitor by an impedance in ohms. This way, a resistor by a real number in ohms, like 30 ohms. An inductor by a positive imaginary number in ohms, like 7j ohms. and the capacitor by a negative imaginary number in ohms like negative 2J ohms. Let's assume that is so, right? So humor me so we can practice. Assume also that we can simplify impedances in series and in parallel the same way that we did with resistors, right? Resistors in series, we add them up. Resistors in parallel, well, you remember, right? Assume also we can apply Ohm's law. We can apply KVL and KCL. We can use M&A. We can find Thevenin. We can use all the things, but with complex numbers. Tutorial time 2. What is the total impedance ZAB of this group of resistors, inductors, and capacitors in ohms seen at the port AB? Write the result in rectangular form. It's going to be a complex number. So you see here, resistors are given by a real number 2, 9, 5 ohms, 3 ohms. Inductors by a positive imaginary number 3J, 5J. And capacitors by a negative imaginary number, negative 7J, negative 4J. So let's assume we can combine them the same way we simplified resistors, right? So let me combine, let's say, if these two in series, 5 and 5J, in series we add them up, and then we put them in parallel with negative 4J, like so. Fine. And now all of that group we put in series with 3. Perfect. And that we're going to put in parallel with 9 minus J7? Absolutely. And then all of that in series with 2 and in series with 3J. That is going to be the total equivalent impedance of that group of elements seen on the port AB. Let's use the calculator to compute that, shall we? Let me move the circuit a little bit to the left to make room for the calculator, and we enter 2 plus 3J. Don't write J3. J3 is a variable, but 3J, the calculator is smart enough to realize that what you want is 3 multiplied by J. You can write J3, but then you have to write J multiplied by 3. Good. So that in series, those two, with the parallel of who? The parallel of 9 minus 7. You see 9 minus 7J, comma, in parallel with what? In parallel with 3, in series with the parallel of 5, 5, and negative 4. 5, 5, and negative 4. And that is the total impedance of that group. 563 plus J 0.22. That is the impedance of all that group. Isn't that sweet? It sure is. Tutorial time 3. Let's assume that we can use Ohm's law. What is the current in the circuit in amps? As a complex number and written in polar form. Let's assume that we can use Ohm's law. Ohm's law? Yeah. Voltage is impedance multiplied by current. Ohms times amps. Or amps are volts divided by ohms. Sure. The current is going to be the voltage 25 volts with 32 degrees divided by the total ohms, right? 2 in series with 7J, in series with negative 5J. We add them up, we divide, and we get, let's do that, 25 with 32 degrees divided by 2 plus J7 minus J5. Enter. That is the current. It has an absolute value of 8.8 and an argument of negative 13 degrees. How do I know it's degrees and not radians? Because I'm here. I see the calculator is in degrees. That is the current in the source and the current in the circuit. 8.84 amperes with an argument of negative 13 degrees. Now tutorial time 4 before we move on into more top hat questions. In this circuit that has two sources given by complex numbers 12 with 30 degrees, those are volts, and 7 amps with negative 25 degrees, you see the resistors are given by real numbers 4 ohms, 1 ohm, and 6 ohms, and the capacitor by a positive imaginary number J, 9 ohms, and the capacitor by a negative imaginary number, negative J, 3 ohms. The question is, the voltage source and the current source are given by complex numbers, and the impedances in ohms of the elements are also given as complex numbers. Assume that you can use Ohm's law, KVL, KCL, M&A, and find V0 as a complex number and write it in polar form. This V0, the voltage in this resistor. Well, Let me move this over here. And the first thing, I'm going to give names to the sources. This is VS1 and IS1. This is my reference node, node 1, branch currents, and write one KCL equation, right? Currents going in, well, it's this one on the left, VS1 minus V1 divided by the impedance of the branch 4 minus 3J, plus the value of the current source IS1, and that is equal to the currents leaving the nodes 1, that is V1 divided by 1, well, that's V1, plus V1 divided by the impedance on the right-hand side, 6 plus 9J. Enter that in the calculator. Let me define VS1. Define it, colon equal, 12 volts with 30 degrees. Remember, the calculator is in degrees, right? Enter. Oh, the calculator is writing that in rectangular mode. Who cares? It is the same number. It doesn't matter how you represent it, right? And let me define IS1 as 7 amps with negative 25 degrees NR2. And now we write a KCL equation, right? So currents going in, VS1 minus V1. Remember to use a lowercase or some symbol that will not collide with the symbols of the calculator. VS1 minus V1 divided by the impedance 4 minus 3J plus the value of the source given by the symbol I defined before, that's equal to the currents leaving the node, that is V1 over 1, well, that's redundant, plus V1 over 6 plus 9J. Enter. That's the equation. Solve that equation by V1. Enter. Oops, I get nothing. What happened? Well, what happened is that I need to set the calculator the right way. Let me go to Shift and the settings of CAS. Down here, I need to allow the calculator to the use of the imaginary unit, like so. And then I go back, and when I type solve KCL for V1, I get an answer. That is V1 in rectangular mode. Let me extract that, and then I can ask for the absolute value of V1C, for the argument of V1C, and I see that voltage, V1, which is V0, has the absolute value of 1.98 volts and an argument of 64.8 degrees, and that is the answer to this exercise. Now it's time for you to show me what you have learned. Let's assume as before that Ohm's law, KVL, and KCL apply. Let's assume that elements are given by complex impedances in ohms, and that the source is a voltage given by a complex number, 10 volts with 30 degrees, right? Assume that. Because Ohm's law, KVL, KCL work, we can simplify impedances the way we used to simplify resistors, right? In series, we add them. In parallel, we invert the sum of the inverses. The first question, what is the total impedance seen by the source? I will ask you that question in two top hat questions. CPX4, what is the real part of the total impedance seen by the source? CPX5, what is the imaginary part of the total impedance seen by the source? Next question, what is the current in the source? In polar form. Question CPX6, what is the absolute value of the current in the source? CPX7, what is the argument of the current in the source in degrees? And now what is the power at the source? The power delivered by the source. You say, what? Well, we are going to compute power this way. The voltage as a complex number multiplied by the conjugate of the current as a complex number. That's going to give me the power as a complex number. So I'm going to ask you two questions. CPX8, what is the real part of the power in the source? And CPX9, what is the imaginary part of that power in the source? And that is that set of questions. Now, before you go, a little present for you, right? You want more? Sure. Find the Thevenin equivalent circuit at the port on the right of this circuit. I'll give you the answer. I'm not going to ask you how this is done or show you. I leave that up to you. The Thevenin impedance is going to be real part 1.7, imaginary part negative 2.8. And the Thevenin voltage has an absolute value of 5.7 volts and an argument of negative 88 degrees. Thank you very much, and I hope to see you all in the next movie. and welcome to Electrical Engineering 202.